Okay, so let me just jump further down. It's not really a rabbit hole, it's more like a slight ditch. There's not much here.
Welcome to Quera's Quantum Capsule. In this
Okay,
video, we'll explore the basics of computing using neutral atoms. Neutral atom quantum computers operate by trapping an atomic vapor in the chamber. Quera
okay.
uses rubidium atoms, but other types of atoms can also be used. Focused laser beams cool these.
Is this like AI generated? Um, it's a little distracting because it feels like the lip syncing is not quite right. So it's a bit distracting, but 19 people like this. I'll make it 20,000 views. Qera trap atomic vapor in a vacuum chamber, cool and control atoms with optical tweezers.
Atoms to near absolute zero temperature,
All
significantly
right.
reducing their motion. Such laser beams, often called optical tweezers, arrange atoms into the desired configuration with great precision. A camera is then used to ensure the atom arrangement is correct. Optical tweezers then replace misplaced or missing atoms. Computation in neutral atom computers begins when lasers excite atoms, lifting them into higher energy levels.
It's very distracting because I keep looking at her lips. Just, I mean, because she says atoms without appearing to say T. What's going on
Do you know
here?
what's really fun? Making a website on Wix.
Yeah, okay. I was like, what's going on?
The design of neutral atom quantum computers, characterized by their all-to-all qubit connectivity, long qubit lifetimes,
Oh,
and
I'm back here.
high-fidelity operations, offers significant advantages. These include scalability to systems with many qubits, the ability lifting them into higher energy levels. This excitation triggers interactions between neighboring atoms. The optical tweezers also allow for moving these atoms during the computation process while
Huh.
maintaining their quantum state. Throughout the computation,
Oh, it's the same thing,
their
it's in
motion,
different
such laser
places.
beams,
Oh my
often
god.
called optical tweezers, arrange.
Okay, that's very confusing. How did I manage to? Okay.
This excitation triggers interactions between neighboring atoms. The optical tweezers also allow for moving these atoms during the computation process
Mm-hmm.
while maintaining their quantum state. Throughout the computation, imaging techniques are employed to measure the state of qubits during the calculation and also at its end. The design of neutral atom quantum computers, characterized by their all-to-all qubit connectivity, long qubit lifetimes, and high-fidelity operations, offers significant advantages. These include scalability to systems with many qubits.
Scalability. Yeah, so she says the B without. Why am I more distracted? This is very distracting. Oh.
Higher energy levels. This excitation triggers interactions between neighboring atoms. The optical tweezers also allow for moving these atoms during the computation process while maintaining their quantum state. Throughout the computation, imaging techniques are employed to measure the state of qubits during the calculation and also at its end. The design of neutral atom quantum computers, characterized by their all-to-all qubit connectivity, long qubit lifetimes, and high-fidelity operations, offers significant advantages.
All-to-all cubic connectivity. So as compared to D-Wave or some of the other ones, I'm guessing it means you can entangle or manipulate any qubit with any other qubit without having to do the weird sort of combinatorial sacrifices that solid-state quantum computers tend to have. Long coherence times, yeah. High-fidelity operations, yeah.
These include scalability to systems with many qubits, the ability to operate at room temperature without cryogenic cooling, and energy efficiency. All of these are
Operate at room temperature without cryogenic cooling. Wait, really? Oh, hold a second.
important factors for advancing quantum computing. Thank you for watching Quera's Quantum Capsule on the basics of neutral atom computing. We invite you to explore our other capsule videos for more insights into quantum technology.
Wait, hold a second. I thought neutral atoms also required cooling. I mean, don't you need a vacuum chamber? How do you create the vacuum chamber without cooling? What's going on? I'm kind of confused. What are the advantages of a neutral atom quantum computer? Like, why am I watching all this stuff? Just watch like a proper video.
In a neutral atom quantum computer, each and every quantum bit is encoded in an individual atom. Quantum bits, or qubits, are the elementary processing and storage units of any quantum computer. And in our case, we use atoms to realize them. We use lasers to trap and manipulate the atoms and let them interact with each other to create entanglement. But why atoms? First, atoms are the world's most pristine qubits. They're all exactly the same. For example, a hydrogen atom on the moon is exactly the same as a hydrogen atom on Earth. Their properties are given by nature, and there's no variance in how they appear. So there's no production variance. This lets us assemble large quantum registers out of exactly identical building blocks already today. And this is important since non-identical building blocks can be a source of error. Second, atoms
Zing!
are extremely coherent. This means that once brought into a quantum superposition, this superposition can be kept unaffected and error-free for a very long time, which is one of the most important prerequisites for quantum computing. In fact, that is why atoms are also used in the world's best clocks. An atomic clock is so precise that two such clocks started at the same time at the beginning of the universe would be off by only about a second by now. Third, atoms are extremely abundant. 1 gram of material contains on the order of 10 to the 23 atoms, such that we will not run short when scaling up our quantum computers.
10 to the 23, that's Avogadro's number, right? So.
And what are the challenges? Like in any quantum computing platform, controlling our system atom by atom, qubit by qubit is the biggest challenge. We have to control a large number of laser beams steered at individual atoms to manipulate their states. Together with our partners in Munich Quantum Valley, we are making great strides in manipulating more and more atoms, moving them in highly complex orchestrated ways, and connecting all the dots towards execution of basic quantum algorithms.
Okay, it's a nice overview video. Came out 8 months ago, 200 views. I'll give them a thumbs up. Yeah. Why not? So neutral atoms, I think that's what the Chinese group used to improve how to arrange it in a grid. Well, I'm a little confused. So they talk about single atoms, but in my understanding, it was more like atom clouds, which is why you know, taking a picture of it to confirm it's there is because it's a cloud. But I don't know. Am I missing something?
Okay, good morning, everybody. It's a great pleasure to be here. And I would like to tell you today about path towards error-corrected quantum computing with neutral atoms. The experiments and results that I will tell you about were performed at Harvard University under the leadership of Misha Lukin in close collaboration between Harvard, MIT, and Quera, Boston.
So it is Misha Lukin. Okay.
Startup. What you see on the right here is not a cartoon, but these are actually sorted atoms in a 2D grid. So I would like to tell you a little bit about how this came about, the basics of neutral atom quantum computing if you want, how we can transport and create single qubits as single atoms that are perfectly identical in nature, and then how we can introduce quantum gates between them, and the recent results that we have had on physical qubit gate fidelities, which we have pushed beyond the threshold for instance, the surface code for error correction. And then I will tell you about some very first results with multiple logical qubits between a few up to 48 logical qubits and first circuits of them that are hard to simulate. I really need to read to you this quote from Richard Feynman in 1983. He said, "Now we can, in principle, make a computing device in which the numbers are represented by a row of atoms with each atom in either of the two states. That's our input. Then the Hamiltonian starts. The ones move around, the zeros move around. Finally, a particular bunch of atoms represents the answer. Nothing could be made smaller, nothing could be made more elegant. This is now 40 years back, and I find it a little bit eerie what Feynman predicted, and I wonder always, did he really believe that this was possible? But this is where we are now, as I will show you. So let me first tell you how we control individual atoms. This goes back to a landmark experiment 22 years ago in Paris. Laser cooling had been invented. People knew how to cool atoms, how to trap them in laser traps. And this experiment by Philippe Grosjean, the only change that he made is he focused the trap to the smallest possible spot that is possible in optics to about 1 wavelength, to the diffraction limit. And he looked at, can we trap atoms in this trap? And what he saw when applying laser cooling was something remarkable. The signal on the bottom that you see here is the fluorescence, the amount of light scattered. There's a lower level, which is basically just background counts on the camera. And then there's another level, which corresponds to 1 atom. And what is remarkable about this experiment was the absence of 2 atoms. You would expect that if you load atoms, there should be a Poisson distribution. So you should also see sometimes 2, sometimes 3, and so on. But 2 or more atoms were always absent. And it was understood already at the time that there's a process. The trap is so tight that whenever 2 atoms come in, there's a light-induced process that leads to a loss of 1 or both atoms, so you end up with 0 or 1 atoms. But when you trap an atom, as you can see, you can hold it over many seconds. So the problem at the time why this didn't go much further is that the probability was only about 50%, and so the probability to trap n atoms, if you want n to be large, is exponentially small. And so what we did in Harvard in 2016 in an experiment was something, the idea was around, but people didn't really believe it would work so easily. So instead of creating a single trap, we used a so-called acousto-optic deflector to create many traps, up to 100 or so. And then we just used simple feedback. We had a camera look at the system determined by the level of fluorescence, which traps had an atom and which traps didn't, and then resorted the atoms. So this is a movie of the first experiments in 1D that we did. This is about 100 traps. These are randomly loaded. And then the computer looks at this, decides which traps are filled, and then moves them over to make almost perfect strings in 1D. And in this way, we could deterministically make up to 50 atoms or so. We then did various experiments with those atoms and then generalized this to 2 dimensions. So here you will see now a 2D grid of a few hundred traps loaded randomly with atoms, and then we can sort them, and you see in each shot the sorting is almost perfect. We had a filling fraction.
Hey, I like this.
For this 225 atom array.
Nice.
And this allows you now to also go to 2D structures. Antoine Brouet's group, who was also a pioneer of this work, also creates 3D structures. He has showed fullerene-like, cone-like, torus-like, and you can see where he comes from in the last picture. So these are 3D structures. We like, however, the 2D structure simply because it gives us easy access along the 3rd direction to address the atoms with laser beams. So we are working mostly with 2D. So you can now trap single atoms, but it only becomes interesting if you can entangle them. And for entanglement, you need interactions between them. And you need interactions over long distances of a few micrometers. That
Quantum gates through Rydberg interactions. Atom can be addressed to create effective spin-half system. We can trap and image individual atoms with optically resolvable separation, a few micrometers. So, I mean, if we're applying, so chips are getting to nanometer scale, and that's what we're saying, they're seeing quantum effects, which is where they're going to hit hard limits, even though they're doing some creative stuff. So you're blowing this up by 1,000-fold, and you're going back to the micrometer regime. Okay.
That we can optically resolve. So remarkably, also about 23 years ago, was a theory paper.
Which again, I mean, initially, that's, I mean, like 1 million of these qubits is, that's millimeter, a meter then. Oh, that's pretty big.
Led by Peter Zoller, Misha Lukin, and others, where they pointed out that if you propelled atoms to very high-lying states, so-called Rydberg states, think of your hydrogen atom with an excited state principal number 100, then the electron is very, very far away from the nucleus. For instance, for n equals 100, the electron is about 1 micrometer from the nucleus. The atom is so big that you could, fit a whole coronavirus inside it if you wanted to. What that means is that the electron is only very loosely bound to the atom, and therefore any tiny electric field or at the presence of any other atom nearby can influence the energy levels of the system. And this leads to large energy shifts of hundreds of megahertz. And of course, the energy shift determines the speed at which you can perform the gates, as I will show you in a moment. So also about 20 years ago, the basis was laid for inducing interactions, quantum gates, entanglement, etc. So the idea is that at about 10 micrometers, this is typical scale. The smallest scales we go to is about 3 micrometers. You have few, depending on the level, on the order of 100 megahertz interaction strength. And that also translates into speed of operation in principle. And these interactions can be used to implement quantum gates over optical.
So 100 megahertz interaction strength or resolvable 5 micron distance can be used to implement strong spin-spin interactions. That's cool, man. I like this.
Resolvable distances so that we can both control the atoms and make them interact. So the idea is as follows. If two atoms are far away from another, let's say more than 10 micrometers, and you try to excite them to the Rydberg state with a laser beam, then both atoms can go to the excited state. However, if the atoms are closer than a characteristic distance we call blockade radius, then once you excite the left atom, then the energy level of the right atom is shifted, and therefore the laser can no longer excite it. But this is also a symmetric situation, so either the left or the right atom can be excited, and that automatically leads.
Only one atom can be excited. Bell state. Oh, it's like, okay.
To an entangled state, so-called Bell states for the experts, or you can use this to create quantum gates between the atoms. So when we understood this, the possibility of this.
So essentially, you're saying this is. So two atoms that are neighbors, or I might have to go back and look at that to see how they did that.
Misha Lukin, Markus Greiner, and I, together with Dirk Englund and John Penner, founded Quera, a startup company that in 2022 basically had a 250 or close to 300 atom machine that is available now for service. This current machine at the moment is an analog computer, but there are strong efforts underway to turn this into a digital machine based on some of the results I will show you in a moment. So what are digital quantum machines? It's basically this idea that you do quantum gates between the atoms, and I think intellectually.
Error correction: encode the same information logical bit in several copies. Physical bits.
One of the, even as an expert in quantum mechanics, one of the most remarkable ideas was this idea that even in the quantum domain, error correction is possible, which is surprising. In the classical domain, of course, you, as you all know, you can encode redundantly your bit into several bits and then take a majority vote and reset any minority bits that have flipped based on the idea that if errors are rare, then it's much less likely that the majority has flipped than that the minority has flipped. But of course, for quantum bits, this is not directly possible because you're not allowed to look at the qubits at all. This quantum state must remain unobserved. And so it's very remarkable that people have come up with various algorithms where you can avoid looking at the state of individual qubits and yet conclude or have an idea whether an error occurred or not. So one of the most famous and most promising codes so far is the so-called surface code that John Preskill also briefly introduced yesterday. The idea is that you encode a single logical qubit in a square grid of physical qubits. In this case, I have used two colors. So half of these qubits shown are physical qubits that store the information, and the other half are ancilla or syndrome or measurement qubits that detect any changes in the state. And so, for instance, if this white qubit has flipped state for some reason,
so computational qubit is empty, so these empty circles. Ancilla error syndrome qubit, the ancilla is the black one, so you alternate. So high threshold for errors.
Due to an error, then the code is set up in such a way that the measurement qubits around it will light up, will change state. And so by measuring the ancilla qubits around it, you can in principle infer that this qubit has flipped. And then without ever looking at it, you can just flip it back. Of course, in reality, the story is not as simple because these operations are not errorless themselves. And so it gets complicated. If you try to detect an error, you have to typically use multiple rounds to figure out, is it really this qubit that flipped or not? The remarkable thing about the surface code, it has a fairly high threshold. Threshold is basically a break-even point. If your physical qubit fidelity is worse, say 2 or 3 or 5%, then as you make the system larger, your fidelity actually goes down, whereas if you're below this threshold, then in principle, by making the system larger, the fidelity goes up. And the logical error scales roughly as the ratio of the physical error to this threshold error times to the power of dimension or dimension over 2, the so-called code distance, which is roughly the side distance of this square.
Okay, so that's what they call surface code. Interesting.
So we first worked on improving the physical qubit quantum gates. So we did 1 qubit quantum gates and optimized them. 1 qubit quantum gates are simply driven by a laser, which takes the qubit from the ground state into the excited state and back down. And we achieved a single qubit operation fidelity with errors of 2 times 10 to the minus 4.
Single qubit fidelity, many copies, greater than 0.9998. Very nice.
Which is sufficiently below the surface code. The bigger challenge was then to do 2 qubit gates. They are harder to do. Initially, we had something like 98% fidelity, 0.98 fidelity. But more recently, by improving our laser system, increasing the power, making everything more uniform, we were able to achieve 99.5% gate fidelity, which is in randomized batch marking, and not only over 1 pair of qubit, but actually in this case 30 pairs of atoms. So over extended large ensembles, we can achieve a gate fidelity, which is now below the 1% threshold for the surface.
Okay, there's a few different gates that you can perform, so I'm not sure which specific gate they're doing, or if this is the worst gate or an average over the gates.
Surface code, and for the first time opens up error detection, and hopefully in the near future also error correction in these systems. Another thing that we tried that turned out to be a very big opportunity in this system is that we entangled pairs, as shown on the left. We brought them close to each other, ran a quantum gate to make an entangled Bell state, and then we transported the atoms over 100 micrometers distances in about 100 microseconds and brought them back. And if we did things right, we could see no deterioration of the quality of the Bell pair. So basically, the stationary qubits and the moved qubits under the right conditions had identical fidelity. So which means that we can now do non-local connections. And even though we are working in a 2D surface grid, we can, in principle, realize 3D, 4D, and higher dimensional structures as well, simply by transport. And this allowed us to do logical qubits. This paper actually just became available.
So I think when he talks about 4D, 5D, I think he's talking about number of particles interacting, not actual dimensions. Well, yeah, dimensions of the calculation, I guess. But
yesterday on the nature side, this in print, and this allowed us to do first experiment with logical qubits in this reconfigurable array. Already a year ago or so, we had done an experiment with a so-called toric code. What you will see here, and you saw this movie yesterday, is you will see 16 stationary qubits, which form the logical qubit, and then you will see moving qubits, which are these ancilla or measurement qubits used to detect errors. And so whenever a red circle occurs, that's when we perform a quantum gate on nearby qubits. And so you see the atoms are brought all the way out, which completes the torus. And then the ancilla qubits are brought to a different zone where they can be separately measured without perturbing the computing qubits. So our measured
show that again.
the
That was a
red
cool
circle
little...
detect errors.
Right.
Which are these of logical qubits in this reconfigurable array. Already a year ago or so, we had done an experiment with a so-called toric code. What you will see here, and you saw this movie yesterday, is you will see 16 stationary qubits, which form the logic qubit, and then you will see moving qubits, which are these ancilla or measurement qubits used to detect errors. And so whenever a red circle occurs, that's when we perform a quantum gate on nearby qubits. And so you see the atoms are brought all the way out, which completes the torus, and then the ancilla qubits are brought to a different zone where they can be separately measured without perturbing the computing qubits. So our vision was then to have two, or I will show you in a moment, 3 zones: a computation zone where you perform a qubits, and then another zone where you can either store or read out the atoms, and maybe a third region where you have atoms to bring in to replace any atoms lost in the process. So this shows you now a system with 3 storage zones that we realized in the recent work: the logical qubit storage zone, the Rydberg entangling zone, and then the readout zone. We code the Rydberg entangling zone.
Zone layout for logical qubit processing. So these are those zones, the layout. So this is storage zone, entangle zone, readout zone. Ancilla qubit reservoir. Syndrome. Extraction. Logical 2 qubit gate. Okay. Local imaging. So I mean, is this a conceptual zone, or like this is within your vacuum chamber that you laid out this way?
And then the readout zone. We could show that as...
So logical C0 with surface code. So okay, so performing a logical C0 with surface code. D is equal to 3, 5, and 7. What does he mean by D? Improved logical error with larger code distance. Surface code distance. So I don't think he means physical distance between the atoms. I think he means how many. Distance is kind of I guess the magnitude, how many atoms you're using. So this is 3 by 3, that's 5 by 5, and that's 7 by 7. And what are these 2 different things is a bit confusing. So as the distance increases, the logical error goes down. Okay?
As we, for the surface code, if we tried to make a C0 gate and made the code distance larger, code distance being larger meaning just using more atoms, larger squares, more physical qubits, up to d equals 7, then we see that with increasing code distance, the logical error actually decreases, as you see in this graph. We also did another type of encoding, which is the Steen code, a color code. We made, in this case, 10 logical qubits, and then we used 5 of those to check on the state preparation of 5 logical qubits, and then we used the remaining 5 logical qubits in this circuit to make a maximal entangled state, the so-called GHZ state, and in the end, we read out all the states, both of the measurement qubits and of the logical qubits. And this movie will show you what it looks like. You will maybe recognize that there are pairs of 7 atoms moving around. Various quantum gates are performed. At the moment, we are realizing the first half of the circuit. And then now the ancilla qubits are moved to storage where they can be read out. And then quantum gates are performed as shown in the upper graph on the rest of the circuits to create a GHZ state in the system.
So they're physically moving these around? So you're literally using your optical tweezers to physically do it. Okay. You're physically moving these around. Interesting.
And what we see, this was not error correction, this was error detection. If we basically condition on having fewer and fewer errors, as shown on the horizontal axis in the plot on the right, then we see that, if we have 20% remaining in the accepted fraction, we have essentially perfect GHZ states of the 5 logical qubits remaining. And finally, we did a circuit where we did a circuit that is hard to simulate. So we used the so-called 832 hypercube code, where qubits are encoded effectively on this 3D cubic structure. And I show you that the movie for this becomes quite complicated to perform, in this case with 12 logical qubits, various gate operations to make a distribution of outcomes that is hard to simulate, as I will show you in a moment.
So I think I was right. So you got to bring the atoms within proximity so that you can overlap them if you want to entangle them, or have them overlap within, I guess, a field or a laser. Okay.
And so if these logical
complex quantum circuits with logical qubits sampling.
We can look at the logical bit string. In blue in front, all the way in the back is the theory, what we expect. For 12 logical qubits, we can still calculate this perfectly. You see that the raw data have some, but very vague similarity with the theoretical results expected in the back, the raw blue data. But as we increase the amount of post-selection, we approximate better and better the expected result for these 12 logical qubits. And what is shown on the graph on the left is effectively a fidelity of the system. So we see that as we reduce the accepted fraction to maybe 15%, we get XCB a fidelity of about 70% in the system. So it increases. Of course, we haven't done yet full error correction in a closed loop, but we are working on doing that next. This is error mitigation. And so maybe I will spend a minute to talk about summary and outlook. We have achieved 1,000 physical qubits. I haven't showed you data, but they're available in the paper where we did experiments of up to 48 logical qubits. Other groups, I think we have seen an example yesterday, and also we have, we are working towards larger system, but 10,000 physical qubits, and I would dare to say even 100,000 physical qubits in these systems are within reach within the next 1 to 2 years. These systems are very easy to scale up because basically while we prepare the atoms, they are not interacting with one another. So preparing more atoms on the side doesn't really affect the atoms in the middle.
Okay.
At 100,000, we meet 2 limits. One limit is the so-called field of view of the microscope. All this is performed under microscope. So if you have a millimeter by millimeter field of view of the microscope, and our typical spacing is 3 microns, you can fit in 100,000 traps. Of course, you can build microscopes just by spending more money with larger field of views, in nanolithography, you can do foot by foot, very large systems with corresponding optics. The maybe a little bit harder limit is the optical laser power. The largest power that we need is for trapping. We need about 1 milliwatt per trap, so 100,000 traps translates into a 100-watt laser. These are available. Trap lasers don't have such high.
100,000 traps require a 100-watt laser. Oh, interesting. So it needs to be the same laser to be coherent with each other? So it's 100 watt. So if you go to like a million, okay, so then you're getting to like a kilowatt. and above.
Requirements as some of the other lasers, but it's possible, and you could, do a few lasers. I think it's already clear that digital quantum simulators will be useful for science. We think that it's very realistic to have maybe 100 logical qubits with errors in the 10 to minus 6 to 10 to minus 8 range within the next 2 years if we push the physical qubit fidelity to 99%. Of course, John Preskill well pointed out that there are still problems to solve. One problem to solve is replenishment of the atoms. However, we think that will work rather in a straightforward way to be continuously reloading atoms. The other problem is the clock speed. At the moment, it's limited by our transport to about 100 microseconds, but we're working actively on that to shorten that further. So for me, I think the hardware that will execute will have, the logical age of qubits, I think, is upon us. Where we really need work and development is useful algorithms that hopefully have exponential speed up beyond Shor's algorithm. And with that, I would like to thank you for your attention.
Somewhere around 2016, 2017, your research group entered the field with neutral atoms. So could you maybe tell us a story? What happened at that time?
One of our first contribution to this field was this kind of idea involving the so-called stopped light. And this idea was based on electromagnetically induced transparency, which actually can be used to slow the light pulses. We realized that this method can be used as a mechanism to store quantum information, to store a quantum state of light. That kind of started this research direction on this stopped light. And I realized that one could actually demonstrate this idea. And this was something which we've done over a couple of months. It's actually landed on the front page of New York Times. But it was very clear at the time that this kind of operation, this kind of light storage and retrieval is actually a linear optical operation. So basically, if you want, can use it for memory, but you cannot use it to process information. To process information, you needed to kind of introduce some interaction, in this case between atoms, because in the light storage process, the state of the light, quantum state, is stored in the atomic excitation. So basically, atoms typically, in the natural state, is a ground state where electron is rotating very close to the nucleus, But actually, if you excite the atoms to the orbit where electron is far away, it actually, the effective size of the atom increases, and then atoms start talking to each other. And this idea of exciting atoms to a Rydberg state is a basic idea behind something which is called Rydberg blockade, which actually, it's also the key ingredient behind this kind of recent wave of, neutral atom quantum computers.
Mm-hmm.
Quick last minute.
Quick last minute change. All right. Okay. So welcome everybody.
Turning neutral atom systems into useful quantum computers. And okay, this is from 10 months ago. I think I'll take a break here.